Okay, welcome back. This is 1.3. I'm going to talk about functions and graphs in a little bit more detail. So I've sort of loosely been talking about functions versus relations. We want to make that a bit more in depth, rigorous, I guess. So section 1, functions and functional notation. And we begin very simply with just what, a relation is a set of ordered pairs. And for example, we could literally write out what our relation is that we want. So let's say 2, 5, the 0.37, 0.49. You could plot those in the XY plane. So it's when we deal with things in the XY plane, usually we're thinking of straight lines and parabolas and that sort of stuff. But this is sort of the most bare bones sort of thing you can have. Let's plot the 1, 2, 1, 2, 3, 4, 5, 3, 7, it's right there, and then 4, 9, it's right there. Okay, so that's relation. Another way you can do these when you only have this like finite number of points is through these arrow diagrams. Okay, so this first sort of bubble is the domain, and you'll list the x coordinates, the first coordinates in each, and here. So 2, 3, and then 4, and then this guy would be the range, and you're going to list all the y coordinates over here, so 5, 7, 9, and then draw an arrow to them if they are in the same parentheses. So 3 goes to 7, and then 4 goes to 9. Okay. So this is the domain, and this is over here is the range. Okay, so a special type of relation then is the function. And for a function, each x value goes to only one y value. So this thing we just looked at here, this relation, is a function. Okay, so a function is just a special kind of relation where each domain value, or x value, goes to only one y value. So maybe what would be more instructive is to look at one that's not a function. Okay, so this is not a function. I'll use the arrow diagram. And again, so I have maybe a different set of domain points. Over here are my range points. And for something not to be a function means that we have one x value going to two separate y values. So in this case, the thing that's preventing it from being a function is this y equals, or sorry, this x equals 2 point here. It's going to two different places. Whoops, went off the page there, sorry. Okay, so this is not a function because of this number 2. It's going in the two places. It's going to 7, and that's going to 8. I notice the 2 and the 3 both going to 8 isn't a big deal for this part. That would mean it wouldn't be invertible. Okay, that means it's not 1-to-1. It's okay, you can have functions that sort of go like this. So this is a function. I'll make sure you can see this one. 2, 3, 4 again. This thing is a function, even though it looks like it's not because you have 2 and 3 going the same place. It's not saying you can only have one corresponding x value for each y value. It's not that saying that at all. It's just saying that you can't have two guys coming out of the x. Okay, so there's algebraic ways to work with these and do proofs with these. We don't do too much of that, but there is always the vertical line test for determining if something's a function. Okay. So if you do have graphing, something that's going to graph your equation, you could kind of tell, or your relation, you could tell if it's a function or not by applying the vertical line test. In other words, if it hits the graph in more than one place, it's not going to be a function. So this guy is a function. The sideways facing parabola is not a function then. Okay. We'll want to be good at evaluating these things, and eventually we'll develop kind of a nice slope formula for nonlinear equations. Okay, so we'll want to have a formula basically that tells me the slope at any point on this curve. Okay, so how do I figure out a slope of this thing? Well, it's variable, and it'll be dependent on the slope of these tangent lines at certain points. Okay, so we won't have a constant slope. This thing is going up, it's going down, but you can take a look at any point on the graph and associate it with the slope of the tangent line to that point. Okay, so we'll want a formula that allows us to find these guys, to find the slopes of these tangent lines, and the beginnings of that formula will be this odd-looking thing, f of x plus change in x minus f of x all over change in x. Okay, and if it doesn't exactly look like the slope formula in the bottom because you have this change in x thing instead of, the original slope formula was y2 minus y1 all over x2 minus x1, right? So when you look at this, yeah, sir, in the numerator I have y2 minus y1, but in the denominator it's like it's not there, right? But it is kind of the same thing. It's just we're calling the x2 minus x1 change in x. Okay, so it's kind of a replacement. Okay, so this thing, we're going to need to be able to evaluate it in order to get our kind of slope formula. And so we'll see problems like number 7, where we have f of x equals x cubed. Okay? And we'll want to evaluate this thing. So what will that look like? I'll have x plus change in x cubed minus x cubed all over change in x. Then I need to sort of FOIL that thing out, right? So I get x plus change in x times x plus change in x times x plus change in x. If you know what is a Pascal's triangle, you can do a lot faster, but I'm getting too old to remember things. So I just go x squared plus 2x change in x plus change in x squared, and then times x plus change in x, and that should give you my final answer eventually. So what am I doing? I'm trying to figure out this thing right here, this part of the difference quotient is what we call this. So distribute, I get x cubed plus 2x squared change in x plus x change in x squared plus x squared change in x plus 2x change in x squared, jeez, plus change in x cubed. Okay, so simplifying this a bit, what do I get? X cubed, got that guy. Do I got any more x squareds? Let's say I got 3 of them. 3x squared change in x plus 3 squared change in x, and then plus there should be another 3 of them, right? So from Pascal's triangle, 3x squared 3x, then change in x squared, and then finally plus the change in x cubed. That'll be all over change in x. And then we can simplify a little bit. I must have lost something, right? Oh, yeah, you still have to subtract away f of x, which is x cubed, so minus x cubed. And then these guys will cancel out. You're left with 3x squared change in x plus 3x change in x squared plus change in x cubed. And when you do these, eventually there's going to be this, what's called a limiting process, where we let the change in x go to 0. So what you're doing is making this denominator, the distance between x2 and x1, be really, really super duper small, so you can pick off the exact slope of the tangent line. Okay, so we'll want to get rid of this change in x in the denominator so that we can plug 0 in, so to speak, to let the change in x be 0. In order to do that, we're going to factor out the change in x's in the numerator. And then cancel that change in x with the denominator, and you're ending with 3x squared plus 3x change in x plus change in x squared for your final answer. The last step would be to let the difference in the x values go to 0. Okay? And you know what's going on there is we're kind of figuring out an average rate of change from here to here, but then letting this x value get super duper close to this x value, and that'll allow us to find the slope of this tangent line. Okay, so you'll let these change in x go to 0, and you'll end up with 3x squared as your final slope formula is what it will be. Okay. So that process is super duper important. Domain and range issues will always be floating about. We're going to be very interested in graphing these things. We want to be able to sort of identify the important bits and pieces. So domains, you remember how this works. It's going to be all real numbers except the places where the x value causes catastrophic failure, right? So except where you have division by 0, you have a negative under an even-powered root, or you have something inside of a logarithm which is less than or equal to 0. Okay? Those are the three main ones I can think of. Let's look at problem 23. And we have f of x equals square root of x plus square root of 1 minus x. Right? So the domain here will be the intersection of the domains of these two particular root functions. So from this guy, first we need to ensure that x is greater than or equal to 0. Okay, and then secondly, from this guy, I need to make sure 1 minus x is greater than or equal to 0. Okay, so solving this inequality here, I'll end up with x less than or equal to 1. And then I need the intersection of these two sets, right? So less than or equal to 1, here's 1. I need anything that's less than that. That'll work in this guy. But then you also need to be considerate of this radical as well. You need to make sure that anything I put in there is greater than or equal to 0. Okay, so the intersection of those two sets, in other words, the overlap, is just going to be from 0 to 1. Okay, so the domain is all real numbers from 0 to 1. Okay, the range has always been a little bit more scuffed, a little bit more in the air, at least for me. I don't know, maybe there's some weird gap in my education where I don't understand how range works, but sometimes, I swear, you just literally have to look at the graph. You know, get your graphing calculator out and take a look. So for example, number 11, I would expect you to be able to kind of finagle this on your own. F of x is 4x squared. So what is this thing right here? Well, the parent graph is the parabola just y equals x squared. Okay? And then if you multiply it by 4, it's going to just stretch it. Okay? It's going to stretch it vertically. So as far as domain and range goes, it will have the same domain and range as the parent function. Okay? So the domain, and there's no division by 0, there's no roots, there's no logarithms, so the domain must be all real numbers. Then the range will go from the vertex to infinity. Okay, so from 0 to infinity. Problem 21, I have f of x equals 3 over x. Okay. So the parent function for this is 1 over x. And if you remember what that looks like, it looks like this. Okay. And this guy, again, will just be kind of a stretching of this thing. And the problem for the domain is division by 0. So we're not going to be allowed to use 0 in our domain. So I'll go from negative infinity to 0 and then union with 0 to infinity. For the range, I won't be able to output 0. So you can see there's a horizontal asymptote right there at 0. It's not that it doesn't, that a horizontal asymptote means it doesn't pass through there. It's just in this case it won't. So again, the range is negative infinity to 0, union with 0 to infinity. I mean, there's no way to get a 0 out of this thing. If you set it equal to 0, there are no solutions. Right? How would I do that? I just multiply both sides by x. Does 3 equal 0? Well, no, that means there's no solutions. Okay. Okay, so in this second case, I kind of cheated. I know what the graph looks like, and so therefore I was able to pick off the range. If you're wondering how did you know this, that it will never equal 0? Well, I cheated. I know what the graph looks like. Right? I had no other way of doing that. Okay, so anyways, you know, how did I know that? Well, how did I know that this was a vertical stretch? Or things like that. Well, this is translation stuff. We're hoping that you already learned these in your beginning algebra class. If not, I'm going to remind you here again. You have a certain number of known equations that you work with, like the line through the origin, y equals m times x, or just y equals x. And then to get other versions of this, you can do translations or transformations. So you'll have a bunch of parent functions, and I've kind of already been talking about it a little bit. This is y equals x squared, and then we have its friend, y equals square root of x. Then we have the absolute value function. So these are all graphs you should kind of already be familiar with. What else do we have? The cubics. Okay, they have origin symmetry or odd symmetry. Then the cubic's friend, its inverse is the cube root function. You know, then your trig functions, so, you know, y equals sine of x, and y equals cosine of x. As long as you know that, you can graph a tremendous number of other graphs just by using the transformations and shifts. So let me remind you of those things. What are they? So if you have y equals f of x plus c, plus or minus c basically, that's going to shift it left or right depending on the sign of c, right? So if c is negative, it'll go right. If c is positive, it'll go left. Okay, so this is left, right. If you have y equals f of x plus or minus c on the outside, then you're going up, down. So if it's plus c, you're going up. If it's minus c, you're going down. If you have a multiple on the outside, you're probably most familiar with thinking of that as a change in amplitude. So it's a vertical stretch or shrink, depending on the c value. If c is greater than 1, it's a stretch. If it's less than 1 but greater than 0, it's a shrink. Then if you have the c value on the inside of the function, it's going to be horizontal, so it'll mess with its period, basically, if you're dealing with sine or cosine functions. Finally, then you have rotations. So y equals negative f of x will be an x-axis rotation. Y equals f of negative x will be a y-axis rotation. Okay. Alrighty then. General, if you get a really complicated composite, you have to follow an order of operations. So it's kind of like doing arithmetic visually, right? So the order of operations, horizontal, stretch, shrink, reflections, and then vertical movements. Okay, so let's try an old trig guy and see how well we remember those. So for example, we have y equals 3 minus 2 sine of 2x. Okay. So as far as horizontal movements, there's not any. So we're in the clear there. Secondly then, stretch shrinks. So we have inside here a horizontal. On the outside we have a vertical. So to figure out the sort of new period, you wedge the guts here in between 0 and 2 pi and then solve for x. Then to get sort of, I always think about my intervals, my tick marks that I'll be using. I just take this interval here from 0 to pi and divide it by 4. So you end up with pi over 4 for your tick marks. Okay. Thirdly, then, we want our this outer portion, so we'll have some stretch shrinks there. So it'll be an amplitude stretch by 2. Then we also have a rotation here, so x-axis rotation. Finally, then, we're going to have to do the vertical, and it'll go up by 3. Sorry, I had a brain fart there. Up 3. Okay. Okay, so let's go at it and see what we're dealing with. So tick marks belong by pi over 4s. Looks like the amplitude is stretched out to 2. There's an x-axis rotation, so originally, you know, it's going like this, and then it's going to flip it, so it looks like this. And then we got a vertical movement up 3, just 1, 2, 3, and then 1, 2, 1, 2. Okay, so we look like this. Oops, I butchered that. So let me try that again. If you need to, you know, apparently I do. You have to go through and kind of 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4. So again, I'm going by pi over 4s. 2 pi over 4, 3 pi over 4, 4 pi over 4. You know, the original graph kind of just dash it in there. It's like that. Then we stretch it. I think I already stretched it. And then I need to flip it. So the flip version will be right here. And then I need to move it up by 3. So I'll have sort of a new center right there. And I'll go down like this, and then back up, and then up 2 more, and then back down. Okay, there it is. Sorry about that. All right. We'll be working with composite functions, and when you make a composite function, you kind of sometimes will change the domain and range. Anyways, let's take a look here. This is section 4. Composites. We'll be worried about inverse functions there here in a little bit in the next section, so we'll need this notation to pull that off. F of g of x is the same thing as f of g of x written this way. So you're putting g of x inside of f of x, and then g of f of x is the same thing as taking f of x and putting it inside of g of x. Okay? So in particular, 67, we have our f of x is x squared, and then our g of x is the square root of x. Okay? Along with finding what the composites are, we want the domain and range. So first I'll start with f of g of x. Okay, so I'm putting g of x inside of f of x. So you'll have the square root of x inside of f of x. The deal with this is, all right, sure, when I square it, it'll get rid of the square root, so I'll end up with x. But the domain of this thing is different than the domain of this thing. So that's one part you have to worry about when you're doing these composite functions, is sort of if you do the simplifications, you lose information, right? So in the original part, the domain, because we have this square root, we need to ensure that our values are greater than or equal to 0. So our domain will be from 0 to infinity. Okay. This example is even more interesting, I think. So this time I want to look at g of f of x. So I'm putting f of x inside of g of x. Right? So I have the square root of x squared. So does this equal x? And no, it doesn't. It's the absolute value of x. Okay. This time, anything goes, right? We could put anything inside of f of x. So the domain will be from negative infinity to infinity. But the output, because it's the positive square root, will always be a positive number. So if you put in -3, you're not going to get out -3. You'll get out +3. Okay, so just remember when you're taking an nth root of an nth power such that n is even, you have to include absolute values. So you may be mystified as you go through your homework and you're seeing these absolute values pop up. It's because this is really is equivalent to this. It's not equivalent to x, unless you are going to restrict its domain. Okay, so just be aware, simplification can cause a change in the domain, with the implicit domain. So it looks like, hey, the domain is negative infinity to infinity. No, it's 0 because of the square root. What else do we have? Even and odd functions now. So this is just y-axis and origin symmetry. Except now you're going to do the tests that are a bit more probably familiar. So for even symmetry, you're trying to see if f of negative x is equal to f of x. And then for odd symmetry, you're trying to see if f of negative x is equal to negative f of x. Okay? So for example, number 80, we have f of x equaling the cube root of x. We want to know if that's even or odd. So if you put in a negative x, replace x with negative x, you get cube root of negative x. Okay? And then you could pull the negative out of the cube root. Okay? And of course, this is just the negative of the original function. So this is negative f of x. And therefore, it has odd symmetry. There's some follow-up questions on translations. So they'll give you the parent function and a translation of the parent function, and then you have to determine kind of what is the formula for the translation. So here I have the parent function given as y equals the square root of x, and then a shifted version of it. And they want you to figure out what this guy is. So I did a horizontal shift to the right 2, so y must equal, manipulate the inner part of the square root, y minus x minus 2, excuse me. Here's one. Is the following a function? Number 49. We have y squared equals x squared minus 1. Okay, so without graphing it, how would I go about determining if this was a function or not? Well, usually if you try to solve for y and it ends up with a plus or minus on the other side, that's a pretty good red flag or indicator that this thing is not a function. Right? But if you remember sort of the criteria for something being a function, for any x value, there's only one corresponding y value. Here, though, note for x equals 1, we're going to get 2 corresponding y values. So when you put 1 into here, you get y squared equals, well, I guess this is the only place you're going to get the 1 at, right? So let's try y equals the square root of 2. Okay? So for x equals square root of 2, y squared will equal 2 minus 1, and then y squared equals 1, and then y will equal plus or minus square root of 1, which is 1. So for the x coordinate in our, if you consider it as a relation of ordered pairs, we would have root 2 comma 1, and then we would also have root 2 comma negative 1. So for one particular x coordinate, you're getting 2 different y coordinates, which is a bad thing. You know, you can even do it as sort of a diagram, your arrow diagram. Here we have radical 2, and it's going to 2 places. It's going to 1 and then negative 1. So that thing is not a function. Okay, so let's call it quits for that for now.